So we ended up asking this question, wouldn't it be great if we could tell how close we were to our goal? So we kind of ended with these couple of slides. So how can we tell if our search is getting closer to the goal? And the idea is that we would create a function called a heuristic. And a heuristic is a function that measures or approximates, that's probably a better word, approximates or estimates the remaining cost till we reach the goal. And so far, we've only thought about the cost of a plan in terms of the number of actions. So in this case, when we first see a heuristic, we're going to think about estimating the number of actions required to reach the goal. And if we look at this kind of puzzle-like environment, if we look at this puzzle-like environment, the number of actions correspond to the number of tiles that need to move. But of course, this is it's an approximation. If we knew exactly how many actions we needed to perform, we'd probably already know how to reach the goal. So instead of actually knowing that, we have to find a way to estimate or approximate. And here we can just look at the two states and say, well, how many tiles are out of place between our current state or our start state and our goal state? So in this case, there are 2 tiles out of place. And therefore, the distance to reach the goal, i.e. the number of actions to reach the goal, is at least 2. So we know those tiles have to move. So that means we have to perform at least 2 actions. We might have to perform more in certain cases. And this function that's returning an estimate of the distance to the goal is what we'll call a heuristic. And the heuristic is something which is calculated from the state information. So the heuristic is the distance to goal. And when we think about this in a search algorithm, we're going to apply this heuristic function, which we're going to call h, typically. We apply that to a state, and it gives us a number back. So this is what we wanted. This is a way of measuring how close we are to the goal. Sorry, I shouldn't say measuring. I should say estimating how close we are to the goal in our search algorithm. And it's really important to take away a couple of things from this. First, it is an estimate. Okay, this isn't the true distance, it's an estimate or an approximation. And the second thing that's important here is that a heuristic often needs domain-specific knowledge. So breadth-first search and depth-first search, for those algorithms, it doesn't matter what the problem is, they behave in the same way. So they expand the tree in the same way every time. That means they are general purpose or domain general or domain agnostic algorithms. They don't care about what the problem is. But when you write a heuristic, what you're generally doing is injecting domain-specific information. You need to know something about the problem and the states in order to write a heuristic. Well, that's at least manually, that's usually the case. And so in this case, we know that the states represent puzzle pieces on the board, and therefore we know that we can count the number of pieces out of place. That is knowledge that we bring as humans to this game. So, given that we've got this heuristic function, we can start to apply it to our search algorithm. So here, we've got our root of our search tree, or our initial state, and we're trying to reach this goal state where all the numbers are around the edge. And we can see that the heuristic function here is 2. As we expand the tree, we can apply this heuristic to the states that we visit, or the states that we see. So on the left, we can see the heuristic is 1. There's only 1 tile out of place. And on the right, we can see that the heuristic is 3. There are 3 tiles out of place. And as we expand the next layer, again, we can see the different heuristic values of these states. And what this means is what we can do, and this should give you an idea for the next algorithm, is that if we use this heuristic information in our frontier, then we can avoid having to look at all the states. We can just use the heuristic information to guide our search algorithm. And that's what we'll do in the next slide. But the key thing, and I repeat this for everyone because it's something that people typically misunderstand, is that, well, maybe let's think about again why we're doing this. We're actually coming up with this heuristic to speed up search. Okay. I haven't said that explicitly, but that's the key idea. We want to find the goal faster. And typically we find the goal faster by looking at fewer states. And we look at fewer states by having some kind of heuristic information that guides us towards states that are closer to our goal. But if the calculation of the heuristic, so once we expand the state during our search algorithm, we will calculate the heuristic kind of on the fly. And if the calculation of the heuristic is very slow, then that will slow down our search algorithm, not speed it up. So we want the heuristic calculation to be quick. And for it to be quick, it typically has to just look at something about the 2 states, the goal state and the current state. And in this case, we're simply sort of looking at the difference. So usually there's a trade-off between how accurate your heuristic is, so how close to the real number of actions it is, and how quick it is to compute. And quick means it doesn't slow our search down, but also inaccurate means it might slow our search down. So we want it to be fast and accurate typically, but usually those things are in tension. The faster it is, usually it's less accurate, and you have to find a sweet spot. So what we're going to do is we're going to go back to our previous sort of set of algorithms. And once again, we're just really going to change how the frontier behaves. So if you remember from last lecture, the frontier is how is the data structure that tells the algorithm which is the next search node to explore, or which is the next search node to add to the tree, effectively, or to build the tree from. Maybe that's the best way to describe it. The frontier is the thing that says which is the next search node to expand, and by expansion we mean adding to the tree. The explored set is the same every time, it just keeps track of the nodes we've seen. And really keeps track of the states we've seen, because we don't want to repeat states. And here we're going to use something called a priority queue. Another name for a priority queue is typically a sorted list. So all we're doing here is ordering the list or the queue such that the value at the front of the list is the value with the lowest heuristic. Okay, so the lowest heuristic value state and search node appears at the start. And that's how we're going to use our heuristic information. So here's a kind of similar example to the end. This is actually sort of drawn from the sliding tile puzzle, but I've sort of thrown away the actual state information. And so now we've got, similar to before, we've got the states or the nodes are numbered 1 to 7. And can someone tell me which state is our goal state on here? Which is our goal state? This is a kind of toy example, and our priority queue, the left-hand side where we pop from the queue, will have the lowest value of the heuristic. So we'll animate it just like we animated before. So we add our root node to the shortest to the frontier. We expand. That creates 2 new nodes, and now they're added to the list, or the list is sorted such that the node at the front has the lowest heuristic value. We expand that, and again we now have the nodes sorted by heuristic value. It means 3 is at the back, 5 is at the front. Then we explore that, and we're happily at our goal. So that is, although it doesn't look much different from our previous examples, the key idea here is we're using the domain-specific knowledge in the heuristic to rule out all these other nodes and focus our search in areas where we believe we're closer to the goal. So I said actually in a few slides back that this was called, so this is sometimes called, let's see if I've got it back here. This is sometimes called best first search. Right. Sometimes called best first search. And the reason it's called best first search is we're looking at what we think of as the best node, the node that's closest to the goal first. We're not looking at breadth or depth. We're now looking at what we think of as the best node. But in actual fact, oops, how do I do that? This is typically now, or more regularly, called greedy search. It's greedy search because it actually ignores some important information. And we'll change examples and talk about that. Oh, sorry, I'm very clumsy today. So we'll go to a different example and talk about why greedy search is called greedy search. So we're going to switch to an excellent Pokemon-themed example, just to make life a bit more interesting. And we're going to have our planning problem looks like this. So again, it's just a lot easier to think about planning problems in terms of navigation or path planning. But planning problems, if you remember from last week, that the planning problem doesn't just have to be about navigation. We can think about battery level. We can think about whether a robot is carrying a package or something. So we've got all these other things we can think about. But to make the examples easy to understand, we'll focus purely on navigation, really. So here we've got Ash, and Ash is trying to reach Pikachu. And we're going to use best first search or greedy search to come up with a path for Ash to follow. So here we're going to use a different type of heuristic. So because it's a different problem, we need a different heuristic. Again, the heuristic is the domain-specific information that we can add as designers, as engineers. So here we use something called city block distance or Manhattan distance. And the Manhattan distance just simply looks horizontally and vertically and counts the distance in terms of grid cells. So we're going to assume the world is divided into a grid, and the Manhattan distance is just looking at the straight line distance in the grid. So we're not allowed to move diagonally. All we're allowed to do and in fact we'll stick to that in this problem, you're just looking in straight line distance. It's called Manhattan distance because Manhattan in New York is laid out in a grid pattern. And so people think of it in terms of city blocks. So here, the heuristic says that Ash is 3 actions away from reaching Pikachu. And so we can build our search node in the same way, our search tree in the same way. And if we follow the heuristic value, so let me just play that up. if we follow the heuristic value, we come up with a plan that exactly matches the heuristic. So we move to the left twice. Now, if you've played a Pokemon game, you will know that you're not actually allowed to walk up those slopes. And so the model of the search shouldn't allow Ash to go in that direction. Now, because we don't live in a video game, we're more interested in robots. And recently I've been doing quite a lot of work with legged robots and quadruped robots. Those robots can move up slopes and can move up steps and paths, but typically it just takes more energy or it takes more time. So instead of saying that the agent can't move in that direction, we're going to be a bit more precise and say, you know what, let's impose a cost. Let's have a cost function. And the cost function will be, if you're on a path, your cost is 1. So if I want to move through that cell where there's a path, it's going to cost me 1. And if I want to move up an incline or an edge like that, that's going to cost me 4. So it's 4 times harder, 4 times more expensive to go up one of those brown slopes than it is to move along the path. And so now we can say that the actual cost of this route is 9. So the heuristic knew nothing about that. The heuristic is just counting the number of actions or the number of steps. And to make it as quick as possible, it's ignoring what the map looks like and just counting straight line. So our heuristic was an estimate which said, we think we're a cost of 3 away from our goal. But in reality, the path that we created was a cost 9. And of course, I've come in and sort of added the cost afterwards, but we can ignore that for the time being. So if we use best first search here, it ignores the cost. And that's why we call it a greedy algorithm. A greedy algorithm just tries to get to the solution as quickly as possible. And you can think of it as being greedy for 2 reasons. And they both mean the same thing, but it depends on how you interpret the word greedy. So in one interpretation, you're gobbling up the distance between you and the goal, right? By always choosing the node that's closest to the goal, you're kind of greedily consuming, chomp, 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 greedily consuming the distance between you and the goal. You could also think about this as greedy because it's ignoring the cost. So it's taking actions without thinking about the consequences. And that is also a kind of way of describing a greedy person, right? They want things, they take them, but they don't think about the consequences. So best first search is a greedy algorithm for that reason. And so we can be a bit more precise as well here. So when we look at greedy algorithms, or when we look at best first search or greedy search, what we can say is that greedy search does not take into account the cost of moving from the start location to a particular node. It only looks at the estimated cost of moving from that node to the goal. Okay? When we look at a state, or we look at a search node, greedy search only looks at the cost or the estimated cost of getting to the goal. It doesn't look at the cost of getting to that start location. And we will see in the next slides, we'll see an algorithm that fixes that. But before we do that, does anyone want to ask any questions?
If we're about to implement this type of technique, I don't know how can we really calculate the cost, in the code level.
Yeah, so typically you'll have some state representation. And in this case, it might be a grid. So your states would be simply a pair of numbers, right? There might be a coordinate frame. So you've got a grid reference, which would be numbers, and you would know the grid reference of the current node, and you would know the grid reference of the goal node, the goal state, sorry. And you could simply look at the absolute difference between those two values. That's what gives you the Manhattan distance, basically. It's if my goal is 3, 3, and my current state is 1, 1, then my Manhattan distance would be 4, because I need to move 2 to the left and 2 up.
I see.
But this is why, like, a heuristic is fast. You want to think about it like that, right? I'm not going to look at the path or anything. Yeah. I'm just going to take my state, which might be 2 numbers, and I'm going to look at the absolute difference between that and some other number, right? You can think of it, if you're an engineer and you think in terms of linear algebra, I think it's the infinity norm between 2 vectors, for example, right? It's not the infinity norm. The infinity norm would be something different, but it's a different norm.
Yeah.
So you want these to be as quick to calculate as possible.
Yeah, that makes sense.
Cool. Anyone else? It's great questions. Okay. So now we're going to introduce a new symbol. So the first thing we had before what we had was an H function that, looked at the estimated cost between the current node and the goal. Now we're going to use something which is the cost of the whole solution. So the heuristic just looked at one part of the solution, which went from the current node to the end. Now we're going to look at a function that describes the whole path. And so we're going to look at an estimate of the cheapest solution that passes through the node. And we're going to represent that as F. Now, greedy search just had F equals H. So greedy search only looked at the cost from the node to the goal. But we want to do this. We want to consider the cost of getting to the node and the cost of getting to the goal from that node. So we want our F function to be a sum between H, which is the heuristic, and G, which is the cost of getting to that node in the first place. Sorry, let me be specific. The cost of getting to the state from the initial state. So it's not about the tree necessarily, it's about the cost of the actions that get you to that state. So this is now how we want to evaluate our nodes in our search algorithm. So you can see that visually if you want. So you can imagine that one of these grid cells here is the current grid cell we're looking at in our search node. And H will tell us how long do we think we have left until we reach our goal. Remember, H is an estimate. Anything you see in pink is a guess. It's an approximation. But G, we know for sure. The cost we know because we've expanded the actions. All right, if I draw this on, no, that's the wrong pen. Oh, I'm sorry. My iPad is being gone to sleep. No. Okay, now it should work. Right. So if we look on the right-hand side, this is a guess. But on the left-hand side, we know because we've expanded these actions. So in the kind of the purpley blue on the left, we know that number for sure, but the number on the right is a guess. And that's how I like to think about this. As we expand that search tree, when we're gaining knowledge about the kind of the initial part of the route, the first half of the route, and we just don't know about the second half yet. And then we just sum those two numbers up, and we can sum them up because they're both measuring the same thing. They're both measuring cost, or their units are both cost. But G is representing known cost, and H is representing the cost to goal, cost to come. So let's apply this. And let's go back to the same example. And now our search nodes have two numbers. We've got the number which represents the heuristic on the left and the number which represents the accumulated cost on the right. So we expand this node, okay? And we could, it generates two, so I'm not going to draw the frontier here, but if something's got a box around it, you can imagine that that is sitting on the frontier. So if it's got a box around it, it is on the frontier. So as before, we start with this initial node on the frontier. We take it off and we generate two children. So the children are what happens if we go left or if we go up. Okay, we're not going to generate all the possible children just to make the slide sensible. And then what we do is we pick the node with the smallest combined, well, the smallest F value, so the smallest sum. On the left, we have 6. On the right, we have 5. So we look there, we expand that node, and we generate two more nodes. One that has an F of 5, one that has an F of 7. So then we expand that one. We take that one off the frontier and add two more. So now we've got one that has 7 and one that has 8. And so at this point, we can look at the frontier and go, you know what? This node looks cheaper now, so let's go back there. And the reason it looks cheaper is because the heuristic is greatly underestimating, right? It's an inaccurate heuristic, and it's underestimating the cost to goal from that state. So we pop that one off and it generates two successors. One which has a cost of 9, or an estimated cost of 9 up here. One that has an estimated cost of 8. So now we know, okay, we've got 9, 8, 8 here. And we've got two nodes that are cost of 7. So typically, this is actually an interesting part of the implementation of a search algorithm. Doesn't always come up in the theoretical side, which is we now have two items in our frontier that have the same value. Okay, they both have F of 7. And you typically you need what's called a tie-breaking rule. You need a way to choose which of these states, which of these nodes do I look at next. And something you can typically do, it doesn't really matter, is if you tie break by choosing the lowest heuristic value out of the F, then you're sort of trying to be greedier a little bit. But because you're still respecting cost, it's fine. So that works quite nicely. What we'll do here is we'll break ties in favor of lower values of H. So that means we'll expand this one. And we expand again, and we get another 7, and we get a 9. So we keep looking at nodes with value 7. And again, we break ties in terms of the lowest heuristic. Do it again, we get another 9 and a 7, so let's look at the lowest heuristic. Do it again, we get another 7 and a 9, we look at the lowest heuristic. Do it again, we get a 7 and a 9, and this time the 7 is our goal state. Okay, so we found our goal. So the key idea here, this kind of covers a lot of interesting things in one example. But what you can see here is that we have expanded, not all, we've avoided expanding a lot of nodes. We did look a little bit at the previous path that we saw. So up here, we did expand this node up the hill. But then we came back and looked at this other selection. One thing that's really important about what we've seen here, and we'll talk about that in more detail in a minute, is that no node that we've looked at has an F value higher than 7. And the cost of the true path has a value of 7. So this algorithm, which we'll talk about in a minute, is called A star. A star is quite an efficient algorithm. In fact, it's optimally efficient. And it never looks at any possible solution that costs more than the true solution. And you can see that here. It didn't actually expand anything that cost 8 or 9. It kept stuck on that 7 route. Okay, so this algorithm is called A star search, and it's one of the most fundamentally important algorithms in AI and planning. If you want to solve a problem, you almost always try A star first. A search problem at least. A star is the kind of go-to algorithm for many applications. Any questions about that? I know that earlier Peidong said that he wasn't quite sure about A star, so maybe there are questions here.
Yeah, so is it true that the search algorithm will get faster when it's reaching to the goal? Or I'm not sure. Because I know initially it's pretty slow because we have lots of possibilities to discover.
No, and
not necessarily.
No, it doesn't. The actual speed of the algorithm doesn't change as it moves through the tree. Okay. Well, a little bit, it depends. So if you've generated, it can almost be the other way around. Oh. Because as your frontier or your explored set gets larger, then you spend time querying those data structures and sorting them. It can cost more later on. But the key idea is that this is much better for finding the shortest path. It'll be much faster than breadth first search or depth first search. So like breadth first search, in fact, you couldn't really apply breadth first and depth first search now because we've got this cost. And now one action doesn't necessarily correspond to one unit of cost. Mm-hmm. But even if it did, if you look, our shortest path is 1, 2, 3, 4, 5, 6, it's 7 levels down. So applying breadth first or depth first search to a tree this big would already be quite crazy, I think.
Yeah.
So it would be much faster than the other mechanisms we've seen.
True.
And it's guaranteed, we haven't talked about this yet, but we'll talk about it in a minute, it's guaranteed to find you the optimal solution. When it terminates with the lowest cost solution. And that's the first solution it will find. It is guaranteed to find first the most optimal solution according to its heuristic and cost function.
So it sounds like a combination of both BFS and the greedy search.
Yeah, so that's a nice way of thinking about it. So it's greedy in that it's looking towards the goal, but it's not greedy because it only looks towards the goal within the set of states that are of low cost. And so it's it expands these nodes in terms of kind of regions of cost rather than so breadth first expands in layers.
Yeah.
A star expands in regions of cost. So what we did is we expanded, and we would have done this. Here we look at the region for which all solutions cost 3. Turns out there's only 1. Now we look at the region in which all solutions cost 5. And now we look at the region in which and still we look at all of the things that cost 5. So you can imagine that's the same as breadth. This is going to be confusing for some people, but it's an interesting way of thinking about it. Imagine that now, instead of having just layers in our tree, each layer corresponds to a cost. And we did the 3s, now we're looking at all the 5s. And after this, we look at all the 6s. And then we start to look through the 7s. And actually, we never go further than 7. So in that sense, it is a bit like breadth first search. But the key idea here is it's a cost. The equivalent for breadth first when you're using cost is called uniform cost search. So it searches an increasing cost. Whereas here in A star, we're balancing cost and heuristic. So Peter asked, are some situations suited for A star? In general, if you can write a heuristic, then A star is a good solution. Almost everybody will use A star for these kinds of problems. The only time it gets worse is if you're dealing with very, 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 very large problems, and then the memory overhead of A star can get too great. So memory, we talked about this last time, memory is actually worse, using lots of memory is worse than using lots of time. Does anyone remember why that was? Why is memory worse than time in an implementation?
Because when you run out of memory, it won't work at all. But if you have memory, it'll still continue to find solution.
Yeah, memory is finite. And time is infinite. I mean, that's a slight exaggeration, but on your computer, memory is finite. And so when you use up your memory, you're done. But when you can't use up time, you might get bored waiting, but as long as you can still use up expand solutions, you're happy. And so when you get to very large problems, you might start to use something like, so one of the go-to algorithms in that case would be something called iterative deepening. And in iterative deepening, you run depth first search, but with an increasing depth limit. So you basically just say, I'm never going to look below depth 5, but I'll run depth first search for that tree. And then if you don't find the solution, you go, okay, now I'm going to look at depth 6 or depth 7, and I run depth first search again. And that has some nice properties, but if you've got a heuristic and you've got enough memory, then you wouldn't use that. Okay. So, where is this? Oh, more questions? Cool. Just scrolling down to see everybody. How you doing? Cool. Okay. So, this is called A star search. It uses the cheapest solution through a node. And if we fill in this plot that we saw before, A star is complete. So it always finds a solution if one exists. It's optimal. So it always finds the shortest path, the lowest cost path. And this plus I put here is because it's optimally efficient. So it is impossible to build a search algorithm that looks at fewer nodes to find the optimal solution. So that's a really cool property. It is optimally efficient, at least in terms of time. But you can see in the worst case, the complexity is as bad as, well, it's almost kind of worse than breadth first. So it's exponential in the max tree depth, not the shallowest solution. So in the worst case, it can be very bad in terms of time and memory. But typically, for most, at least at this stage in your careers, you'd be caring about these things on the left. It's optimal, it's efficient, and therefore it's the algorithm that you typically want to use. The downside is that you have to write a heuristic, but usually most problems have a reasonable heuristic. And if not, what we'll see maybe today, maybe another lecture, is there are ways of automatically computing heuristics for some problems. And so for some problems, and that's nice because for the algorithm we saw here, because we had to write the heuristic, it was not a domain general algorithm. But if we could calculate that heuristic automatically, then we could come up with a domain general algorithm as well. So A star is optimal, but that doesn't mean it doesn't get that for free. So it's what I've written is not omniscient. It can't see everything. So that means there's actually an important constraint on the heuristic. And I've already mentioned it, but it's probably just worth throwing it in again. So A star relies on what's called an admissible heuristic. An admissible heuristic never overestimates the cost to the goal. So I said this a bit earlier. Our heuristic should be a lower bound or an under approximation of the cost. We can never return a number that's greater than the cost to the goal. If we do, then A star no longer becomes optimal. So, in fact, this describes the regions, but that's less useful. Just a final slide on A star to motivate why this is. So this is the same graphic that you saw with Ash. We've got some initial state or node. We've got some goal node, or goal state and node. And we've got N, which is the current node we're looking at. And we are looking at the nodes which are a sum of G and H. G is on the left-hand side. It's this fixed edge, and H, remember, is a guess or an estimate. It's on the right. So we can imagine what happens when we know the real costs, right? So let's look at two examples. We've got two nodes, N1 and N2. And these two pictures show, let's say, the real cost of the solution if we actually knew the correct value of H. So here, N is a little way away from G, but actually the overall path is shorter. In this second node, N2 is very close to the goal, but the actual overall path is a lot more expensive. So what happens if we've got a heuristic that overestimates the cost? So in this case, our heuristic's really bad and returns a value that is like 4 or 5 times what the cost is. So in this case, what we can see is if we overestimate and return an H that's 4 or 5 times the true cost, this pushes the overall path length out here. But if we do the same for this example where there's a short path length, we can see that node 2 looks better than node 1 because the combined distance is smaller. But in reality, node 2 is much worse than node 1. So this just shows you what happens if you incorrectly estimate or incorrectly overestimate your heuristic. You can end up returning solutions that are no longer optimal. Well, your algorithm is no longer optimal. You can no longer return the optimal solution. Any questions about this? This is a kind of technical requirement for A* to work. Okay. So, what we've seen today are graphs, and last week, graphs, trees, search, and heuristics. And these ideas really underpin almost all of planning in different ways. And we'll see that when we look at kind of deterministic planning. We'll look at it when we see planning under uncertainty, when we look at motion planning. These are all going to be search, but importantly, they change the type of model that's used. So here we just assumed a kind of graph or a tree, we looked at grids, didn't we, as well, as types of models that we were searching over. When we move to these other types of planning, we'll also look at different types of models. And this is a good time. We will switch to the next set of slides. What I'm going to suggest is that we all just take a 5-minute break just to help your concentration. So